In this video, we'll work through examples involving Le Chatelier's principle. Le Chatelier's principle describes how a system at equilibrium will adjust or shift to restore equilibrium when a stress is applied to the system. I want you to think about these problems in 3 stages. First, identify what the immediate effect of the stress is on the equilibrium. Are there momentarily too many reactants or too many products? In the case of a change in volume, is the overall pressure too high or too low as a result of the change? If a substance is added that is not part of the equilibrium system, is it an inert substance or a catalyst? Or will that substance react with something in the equilibrium system via a side reaction? If a side reaction happens, is the immediate effect that we removed reactants or removed products? The next thing you do is decide what needs to happen before you think about the direction of the shift. For example, if there are too many reactants momentarily, then in order to restore equilibrium, more products will need to form. And finally, based on what needs to happen, in which direction will the reaction shift to restore equilibrium? If more products need to form to restore equilibrium, then the reaction will shift to the right. Here are the general trends that you should understand. Adding a substance that is part of the equilibrium system will push the equilibrium away from that side toward the other side. Removing a substance that is part of the system will pull the equilibrium toward that side, away from the other side. You'll see how this works when we look at the example. Adding a reagent that reacts with a substance in the equilibrium system will remove some of that substance from the equilibrium and pull the equilibrium toward that side. This effect is the same as removal of a substance. It's just indirect due to the side reaction. Changing the volume will cause the equilibrium to shift to whichever side will restore the overall pressure. When you encounter volume changes, first identify what happens to the pressure. For example, if the volume increases, then the overall pressure decreases, as described by PV equals ZRT. Since the immediate effect is that the overall pressure decreases, then the equilibrium needs to adjust to counteract that effect, and it will shift in the direction to increase the pressure. According to PV equals nRT, if we increase the moles of gas, the pressure will increase. So the shift is toward the side with more moles of gas. And you determine this by adding together the balancing coefficients for the gaseous substances only. Adding an inert gas or catalyst will result in no shift. An inert gas is neither part of the equilibrium system, nor is it something that will react with a substance in the equilibrium system. It is inert, so no shift occurs. Adding a catalyst would only serve to increase the rate of the reaction and speed up how fast this system reaches equilibrium. The system is already at equilibrium, so adding a catalyst has no effect. The last stress that can happen is changing the temperature, and the effect depends on whether the reaction is endothermic or exothermic. This is the topic of another video. So let's work through some examples. All of our examples are going to refer to this equilibrium system. And for each stress, we're going to go through that strategy. We're first going to identify the immediate effect of the stress. We're going to decide what needs to happen to restore equilibrium, and then we're going to determine in which direction the equilibrium will shift based on what we decided. So in our first example, NO2 is added. So we take a look at our equilibrium system to see, is NO2 part of that system? And it is. NO2 is a reactant. So we're adding NO2, which is right here. The immediate effect of adding NO2 is we have too much NO2, which means we have too many reactants. That's the immediate effect of this stress. In order to restore equilibrium, which has now been disrupted, the equilibrium needs to shift away from the reactant side and toward the product side. In other words, we need to form more products. So if we have too many reactants, the change that's needed is we need to form more products. And if we need to form more products, then the shift is going to be towards the product side, and it will shift to the right. In our next example, HNO3 is added. So we look to see if it's part of the equilibrium system. It is. It's right here. It's on the product side, so the immediate effect is too many products. In order to restore the equilibrium, if we momentarily have too many products, then we need to form more reactants. And the direction of the shift will be towards the reactant side. So the reaction, or the equilibrium, will shift to the left. Next, we have a situation where H2O is removed. So we look to see if it's part of the system. It is. It's right here as a reactant. It's removed from the system, and the immediate effect is we have removed some reactant, and so we have too few reactants, not enough reactants. If we momentarily don't have enough reactants, then what needs to happen is we need to form more reactants. And in order to do that, the equilibrium will shift towards reactants or will shift to the left. Here, we're told that NO is removed. So we look for NO, we find it over here. It's on the product side. We have removed product, and so the immediate effect is too few products. In order to restore the equilibrium, we need to form more products. Which means the equilibrium will shift to the right. Now we're looking at a volume change. So we're told that the volume is increased. The first thing we want to do is identify what the effect is on the pressure. So if the volume is increased, that means that the pressure, the overall pressure, had to decrease. In order to restore the equilibrium, we need to restore that pressure, and we need to increase the pressure. In order to increase the pressure, the equilibrium will shift towards the side that has more gas particles. So it will shift to the greater number of moles of gas. How do we figure out which side that is? We add up the coefficients on each side for the gas substances only. So on the reactant side, we have 3 plus 1 gives us 4. On the product side, we have 2 plus 1 gives us 3. So the equilibrium will shift towards the side that has 4, and it will shift to the left. In this example, the volume is decreased. So we're going to go through that same logic, that same approach. The volume is decreased, so we want to know what is the immediate effect on the pressure. If the volume is decreased, then the pressure increases as a result of that change. So if the pressure increases, then it is momentarily too high. And if the pressure is too high, the equilibrium will need to shift in such a way to lower the pressure. So we do the same thing that we did last time. We count the number of moles of gas on each side, and the lower pressure side will be the fewer number of moles of gas. So as we just counted in the last example, we have 4 moles of gas on the reactant side, 3 moles of gas on the product side. So the equilibrium will shift towards the fewer moles of gas, and it will shift to the right. In this example, we're told that O2 is added. So we go through our same assessment. We take a look at the equilibrium, and we look to see if O2 is part of the equilibrium system. And it is not. We then look to the additional information that we're given, which is there is another known reaction that occurs under these experimental conditions. And we find that O2 is part of that. Importantly, O2 will react with NO2. So we look to our equilibrium system to find if NO2 is there. And it is. NO2 is a reactant. So if we add O2 to the system, it will react with NO2 and form N2O5. Now my notes don't reflect the stoichiometry. I'm just trying to show that NO2 is removed as a result of that side reaction. Now the effect is that we are consuming some of the NO2 because some of it is being used up in this side reaction with O2. The immediate effect is too few reactants because we've used up some of our reactants in this reaction with NO2, this side reaction with NO2. So if momentarily we have too few reactants because of this side reaction, then in order to restore the equilibrium, we need to form more reactants. And if we need to form more reactants, then that shift is going to be towards the reactant side, and the equilibrium will shift to the left. In our next example, neon is added. So we look in our equilibrium system to see if neon is there. It is not. The next thing we do is identify if there is a side reaction, if neon reacts with something in our equilibrium system, and it does not. So based on those two factors, we determine that neon is an inert substance and does not react with anything. And the immediate effect of adding neon is that there's no effect. And if there's no effect, then there's no shift. In our next example, we're told that a catalyst is added. Now we're not given the chemical formula, and so we assume that it is something external to the equilibrium system. In other words, it is a different substance. So it's not directly part of the equilibrium system. The other thing we need to remember is that the sole job of a catalyst is to speed up a reaction. It makes the reaction happen faster. In the case of a reversible system, an equilibrium system, it is going to speed up the reaction so that equilibrium is reached faster. However, the system is already at equilibrium. So the immediate effect is that there's no effect. And nothing needs to happen to restore the equilibrium, and there is no shift.